So hi again everyone. So I'm back now for the second part of the tutorial 7, which deals with the question 2. So with this question, we are looking back again at the time-temperature correspondence for polymers. So in this specific problem, we know that we have one polymer, that is PMMA, or polymethyl methacrylate. And PMMA, at 115 Celsius degree, has a relaxation modulus of 0.1 GPa after 3 times 10 minus 4 hours. Okay? So if you want to rewrite it in other terms, you could just say that generally that the modulus of a material at a time and a temperature is equal to a certain value. So in this specific system, we would write this as E of 115 Celsius degree. I will put this on the right at 3 times 10 minus 4 hours, and 115 Celsius degree is equal to 0.1 gigapascal. Okay? So this is the way you can just rewrite all of this first part of the problem. So now, what we want to know from this problem is we want to calculate the time that we need for this polymer, this PMMA polymer, to reach the exact same relaxation modulus when it is placed at a temperature of 130 Celsius degree. So the first thing that you can think about when you have this kind of problem is that you look at this and you see that 130 Celsius degree is higher than 115. Okay? So what does that mean? It means that the PMMA will likely be softer because the temperature is higher. So we would expect the time to be also shorter. So we should have something below 3 times 10 minus 4 hours for the polymer to reach this relaxation modulus of 0.1 gigapascal. So if you remember in the last tutorial, I introduced the concept of WLF equation. Okay? So this WLF equation states that the log of AET is equal to minus C1 of the temperature of the polymer minus the glass transition temperature of the given polymer. Okay, so that's what we stated. Okay, that's the relationship, the WLF equation. Okay, of which we know the constant C1 and C2. So we know that C1 is equal to minus 17.4, and C2 is equal to 51.6. Okay? So we know the constant C1 and C2. So now we can start to take a look a little bit at what is the meaning of this AET, this shift factor that I described last time. So you can write AET as the time you can write this AET like this. Okay. So what does it mean? This actually means that AET is equal to the time at which our polymer relaxation modulus will be equal to a given value. Here 0.1 GPa, and at which temperature? So so if you write it like this, T of T1 and T of Tg. Okay. So for this, you basically define an arbitrary modulus. So for a modulus for the material to reach a modulus, say, of 0.1 GPa, or 0.01 GPa, or etc. Right? But the point is that we are trying to define here the time after which this PMMA material or this other material will reach this specific modulus at T1. Okay? And to rephrase it again, for this TTG, is the time after which the material, here PMMA, will reach a given modulus at the temperature Tg. So this is how you should read it. So make sure that you understand this. It has to be very clear to be able to approach this kind of problems in the different ways you might have to later. Okay. So now, if you consider the information that we have, we are asked to get basically T of 130 Celsius degree. Okay? So we want to know the time for which we will get the time after which we would get a modulus of 0.1 GPa at 130 Celsius degree. Okay? So if you were to use this expression, you would write it like okay. So now, when you look at the information we are provided, we see that we have a problem here. So we know the glass solution temperature, but we don't know after how much time our material will reach this 0.1 gigapascal relaxation modulus at the glass solution temperature. Okay? So we do not know this. And of course, since we are asked to calculate this, we don't know it. So with this expression as such, we cannot solve the problem. So we need to look at the information that we are given. So we know that, we know this, right? So this is something that we know. So it means that we know that T at 115 is equal to right? So we know that. So it means that we can perhaps use this to be able to calculate the time for the PMMA to reach 0.1 gigapascal relaxation modulus at the glass solution temperature. So if we're able to calculate this, then we can easily solve all this problem. It's just a matter of plugging the temperature in the WLF equation. So I hope the approach is understood. We are just going to derive the expression we are just going to derive this expression to get to the temperature at glass transition time, the time after which our polymer will reach a modulus of 0.1 gigapascal at the glass temperature. So if we calculate this, we can now get here and calculate this. Okay? So I'm going to erase those information, and we are going to start with the solving of the problem. Okay, so let's start as we just discussed. So we say log of time at 115 divided by time at Tg is equal to minus 17.4 times the temperatures. So we have divided by okay. So just one thing here, I'm just expressing, so the temperatures are supposed to be expressed in Kelvin, okay? So you would have to add a 273.15, but knowing that we are just calculating the difference, anyway the result won't change if we work in Celsius degree or Kelvin. So that's why I decided to go with this method, just putting them directly in the equation in Celsius degree. But just for you to be aware, these values are supposed to be expressed in Kelvin. So let's continue with this. So we obtain, if you just calculate this, we obtain a value of minus 3.92. So now we just need to solve this log equation, right? So we say that 3 times 10 power minus 4 divided by the time, after which our PMMA will reach a modulus of 0.1 GPa at the glass solution temperature is equal to 10 power minus 3.92. Okay? So we can say that okay, and so we get a time of approximately 2.49 hours. Okay, so we get a time of approximately 2.49 hours. So that makes sense, right? Because since we are looking at a lower temperature, the TG is 100 Celsius degree. We are expecting that the time will be longer. If you remember the explanation that I gave earlier, we're expecting the time to be longer because the material is not as soft if you are using temperatures that are lower. And this is what we get. From 2.49 hours at 115 to 3 times 10 minus 4 hours at 115. So you can also see the magnitude of the change, right? Just by increasing of 15 Celsius degree, if you put them into a setting of stress relaxation, you have a very large difference in time after which the polymer will reach this specific relaxation modulus. It's very quick. Okay, so now let's continue. So now that we have TTG, we can start to work with the second equation. So let me erase this. Right. So we would write this as all right, this is how we would write it, and now we know TTG. Okay. So for which we obtain a value of minus 6.397. So now if you look at what we know, we get to the following expression. And so now we can calculate the time after which the polymer will reach a relaxation modulus of 0.1 GPa, gigapascal, at 130 Celsius degree. So we do the same thing as what we did before. and we get a value of 9.9 times 10 power 7 hours times 10 power minus 7, hours. So you can see that within a window of 100 Celsius degree, it took for us 2.49 hours. At 115, we just need 3 times 10 power minus 4 hours. And now at T, we need so you can see how fast the time changes. The effect of the temperature is quite drastic on the viscoelastic property of polymers over time. So that's it for today. So this is question 2 now. So if you have any questions, again, don't hesitate to send me an email, and I will reply to the best I can when I receive your emails. So I'm very open to any discussions or questions related to the tutorial. So please do not hesitate. Thank you, everyone, and have a good day.